Hi everybody, welcome to another video in Calculus 2, section 6.2, area between curves. So pretty much we have two functions and the function are continuous. We have one function greater than or equal to the other function. So pretty much what we have is f of x is greater than or equal to g of x. So the function f of x is the function on the top. Function is above, and that is the upper curve. G of x is less than or equal to f of x, so the graph, the curve is going to be below f of x. So we have the lower curve. And we want to find the area from A to B, from x equal to A to x equal to B, and we want to find this area. So in that case, we just set up the integral for the upper function minus the lower function. The limits, those are given, and we just integrate. Whatever it is the area between the two curves. Like I said earlier, very straightforward. So there's a little note here. The first, we talk about area, and it is bounded by the graphs from A to B. So when we talk about area, area cannot be negative. And then after that, the area here be equal to the upper function minus the lower function. So the upper function minus subtract the lower function, and we integrate. That gives us the area between the curves given by the two functions. Right, straightforward. Now let's look at the first example. Set up the integral, then use the calculator to calculate the area bounded by those two functions, and then the y-axis. So first, we have f of x equal to 4 over square root of x plus 1, and we have the graph here already. So that is f of x with that curve. Next we have the equation, the curve or the linear function g of x equal to x minus 1. So that's just a straight line. And then we also have the y-axis. So the area that is bounded by those three curves. So we're talking about this area. So, and first when we look at this, we see that the point here is 3 and 2. So x equal to 3, y equal to 2. The y values doesn't matter because we integrate with the x. So the area equal to, all the x values of this area go from 0 to 3. So that will be the limit. And then we just have the function that is above minus the function that is below. So when we look at this, of course the one above is the curve, the one below is the line. So the curve, the function above is 4 over square root of x plus 1. That is the function above. Subtract the lower function or the function that is below, is x minus 1. And we integrate. So we just use a calculator here to get the values of the integral. So let's just clear off this. So first we just do the integration. In TI-84 calculator we hit math option number 9, and that is the integral that goes from 0 to 3. And then we have the function. I can enter the fraction as alpha y equal, and then enter. That gives us a fraction 4 over square root of x plus 1 and then subtract x minus 1. And we have 6.5. Which if we change to fraction, math to fraction, that is 13 over 2. Right, so that's simple enough. By the way, if you use in TI-83 or different model of TI-84, it might not look like this. Right. So what we can do is hit mode, and if you have an option to have the math print, keep that. If you cannot do anything, if it did not have the option of choosing this, that means it is in the classic mode. So when you hit math option number 9, it will be like this. Don't worry though, the syntax is still the same. It looks a little more difficult to read, but it calculates the same thing. The math is still the same. So we have the integral, the integrand, and then x is the variable that goes from 0 to 3. Of course, it is the same thing. So once again, we need the function, the integrand, x, and then the limits. I will switch back to math print. Right, so just have that. So upper function minus lower function, and then the limits. Pretty much it. Next, find the area bounded by the graph of this, and that. So first of all, the function f of x equal to x plus 3. So this is a linear function. So we do with just linear function, a line. So we need 2 points. And y, or f of x, equal to x plus 3. When x equal to 0 plus 3 is 3. X equal to 1 plus 3 is 4. So we have the line that has the point 0 and 3, 1 and 4. So draw the line. And so that is y equal to x plus 3. Next, what is the graph of absolute values of 2x? So first, absolute values of a is going to be itself if it is greater than or equal to 0. It is equal to opposite if it is negative. Because absolute values is the distance to 0, so the distance cannot be negative. So if it's positive, it will stay. If it's negative, it will turn opposite to that, which will be positive. Right. So absolute values of 2x is going to be the same if 2x is greater than 0, or if x is greater than or equal to 0, or it equal to negative 2x if x less than 0. Right, so we have two parts of the function. First one, 2x, x equal to 0, y equal to 0, x equal to 1, y equal to 2, x equal to 2, y equal to 4, and then so on. And then negative 2x, x equal to 0, y is 0, x equal to 1 is negative 2. So the one on the right is y equal to 2x. The one on the left is y equal to negative 2x. Right. And we want to find the area bounded between the two graphs, so we're talking about this one. Right. So first, if we want to, we can use absolute values, but usually if we do it by hand, is absolute values is usually it's not going to be the case. So first one, we need to find the intersection. Y equal to x plus 3 and y equal to negative 2x. We make them equal each other. Just going to do that quickly. X plus 3 equal to negative 2x, for instance. Move the x over, move the 3 over, and divide by pretty much x equal to negative 1 here. So that's why we have this intersection at negative 1. And then similarly, we make x plus 3 equal to 2x. We have equal to 3. So the limit will be from negative 1 to 3 if we talk about the function. So we can set it up like this. The area is equal to integral limits negative 1 to 3. The function above, the upper function, is x plus 3. So if we looked along the y-axis, look in that direction, so we will see the x plus 3 on the top and the absolute values at the bottom. So we essentially we can set up with the upper function is x plus 3 the lower function is just absolute values of 2x. Let's use calculator for this part. Math number 9, that goes from negative 1 to 3. We have x plus 3, x plus 3, subtract absolute values, math, numerical, absolute values. We can either do that or we hit alpha window absolute values and of 2x, and let's integrate. so that equal to 6. Right. However, if we do it by hand, we'll never integrate of absolute values. We have to write that as positive and as negative. So bottom line is, when we look at this one, it is bounded above by y equal to x plus 3, but the boundary below, the lower boundary, consists of two functions. One of them from -1 to 0, the function below is -2x, whereas when x go from 0 to 3, the function below is 2x. So because there are two boundaries at the bottom, we need two integral. So either we do this, not very practical because of the absolute values. We can say if we go from -1 to 0, for this part, the function above is x plus 3. The function below is -2x. So that is this area here. The other area is another integral, but this time go from 0 to 3. The function above is x plus 3. The function below this time is 2x. So since this one is simple enough, I'm just going to do this. So -1 to 0, x minus -2x, so that is 3x plus 3. And then x minus 2x is minus x plus 3. Right. So when we integrate, integral of 3x plus 3 is 3x squared over 2. And then plus 3x. Integrate from -1 to 0. So that's the first part. The second part is integrate of that, which is just negative x over 2, x squared over 2. Plus 3x. That go from 0 to 3. Right, and then we just put in the limit and subtract. So we have put in 0, we have nothing. Subtract. Put in -1. Plus 3 times -1. And then plus, put 3 in for x. And put 0 in, we have nothing. So we have negative -1 squared, so still 1, so 3/2 minus 3, and then add -9/2 plus 6. Right, -3/2 minus 3 plus negative 9/2 plus 6. It will live. Is there any? Why it's not 6? Minus 3 plus 9/2. Yeah, we put 3 in here. That should be 9 side. Yeah, that should be 6. So yeah, so we put 3 in for x. So that should be 3. Sorry. Right. So that those are samples. Right. So that the area bounded by a function above, the function below. And next, also the area between two curves. However, this time the curve is we're going to do it horizontally, meaning with respect to y. So we still have the function f greater than or equal to function g from the interval from c to d. So in that case, we have the function, that one is the function on the right minus the function on the left. So we just say the integral from c to d equal to the function on the right, which is the bigger function. Subtract the function on the left, which is the smaller function with respect to y. So so we have the function on the left, function on the right. The right function is bigger, so the right minus the left, because this is the area supposed to be positive. Right. So let's look at the first example here. I'll find the area of the region bounded in the first quadrant. So don't forget that this is in the first quadrant only. Bounded by the curve y equal to x cubed. X cubed, of course, look like that. And so let's look at y equal to x cubed. Let's pick some value for x and then find the corresponding values for y. Negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. We can also look at the table where we enter the function y equal to x cubed, and then the other function is x plus 6. And then instead of hit the graph, of course we have the graph too, but let's look at the table. So second table, of course we have those values. Yeah. Right. Notice that this is the area in the first quadrant only, and that's very important. So we have the graph. So that this is x cubed and then next y equal to x plus 6. Sorry, this is a very bad problem. I think there's a typo here. Right, so there's a typo. So either we have the first quadrant or we have the x-axis. So let's determine. I'm going to drop. I'm going to change in the note, so don't have to worry about it. So find the area of the Reagent. Just ignore that completely. Yeah. This is the problem. So we do have the x-axis. Y equal to x plus 6. X equal to 0, y equal to 6, x equal to 1, y equal to 7. Yeah, so ignore the in the first quadrant part. Yeah, so this is y equal to x plus 6. Right, and then the x-axis, which is y equal to 0. So we have three functions, and we're talking about the area here. Yeah, sorry, it should not be that first quadrant. Right, now if we look at the area here, let's say if we're still using like what we did earlier, dx. So if we look from the bottom up, we see for those regions, the function below is y equal to 0, the x-axis, the function above x plus 6. So the boundary is consistent from -6 to 0. However, starting from 0 to 2, the lower limit is no longer the x-axis, but the x cube, because there are two boundaries at the bottom, one boundary on the top, two boundaries at the bottom. Make that if we're going to use dx, it is going to have two integral. So one of which going from -6 to 0. By the way, let's look at the graph, because same thing. From -6 to 0, we see that the function above is x plus 6. So x plus 6 is on the top. The function below is the x-axis, or y equal to 0. I'm just going to put it like that. And then dx. So that's for one of them. The other one is when x goes from 0 to 2. The reason we know that it goes from 0 to 2 because when we look at the intersection, that point is x equal to 2, y equal to 8. If we actually want to find the intersection, second, calculate option number 5, intersection. Right, ask you, is that the first curve? And it says yes. Is this the second curve? Also yes. Right, what is your guess? We're going to move close to the intersection. When we hit enter, it will jump right into it and say x equal to 2. Right, so or we can just go to the table here, and we see when x equal to 2, the y values are the same. So indeed, it is 2. So we go from 0 to 2. The function above is still x plus 6. the function below is x cubed. So if we're going to use dx, we have to split the integrals because there are two limits at the bottom. Right, so let's just do that quickly and see what we have. We go from -6 to 0, and integral just x plus 6. By the way, this is a triangle. I can tell you is 1/2 base times height, 6 times 6 divided by 2, so that is 18. We don't even need the integral. If we want to, of course, that's 18. Right, and then we have the integral from 0 to 2, math number 9. That go from 0 to 2. And we have x plus 6 minus x cubed, or xxx. And all together we have 28. Right, so that is one way to do that. Or now, instead of looking along the y-axis, we can look this way along the x-axis. In that case, if we look we go bounded on the left by this function, bounded on the right by the curve. So in that case, if we set up using dy, we only need one integral, and the y values where it goes to. Notice that the point here is 2 and 8. So the maximum y values for the region is 8. So we go from 0 to 8. And we have the function on the right minus the function on the left. The function on the right is x cubed. But notice that when we do this, this is going to be dy, right? So the limit is for the y values. The function have to have y in it. You cannot put x in here. That will not work. So you have to have y only here. Or even constant, still fine. But you cannot put x in here with the dy. That will not work. Right, so how do we do that? Right, y equal to x cubed. Can we write x in terms of y? And it's simple enough. If we have y equal to x cubed, we will take the cube root on both sides. So the cube root and the cube cancel out. We have cube root of y equal to x. So when this y equal to x cubed, equivalently we have x equal to cube root of y. And we're going to use this function because we need y. We don't need x. So right, x is a function of y. And then when we have y equal to x plus 6, this one easy. Subtract 6 on both sides. X equal to y minus 6. And we're going to use that function. So the function on the right is x cubed, but we cannot put x cubed. We have to put the function of y. So that will be cube root of y. And then subtract the function on the left, y equal to x plus 6, but we have to write that in terms of y. Minus 6. Right, so if we integrate, we can use x or y. It doesn't matter when we use on the calculator, but I'll just keep y. So we get the cube root, math, option number 4 for cube root of y, alpha 1 minus alpha 1 for y minus 6. And that should be 28 as well. It is 28. However, when the calculator does the computation. It's just an approximation calculator. This calculator cannot integrate. It can only estimate the area. And then there's some machine error here. So I have to expect that to be just 28. Right, so that. So if we have dx upper function minus lower function, if we have dy, it's going to be a function on the right minus a function on the left. Right, some example here. So first, set up the integral that calculates the area of the region in the first quadrant bounded by those two functions. So first, let's see how that look. Y equal to x to the 2/3, x to the 2/3, and the bottom x minus 4. Let's look at the graph. It's going to be that. Right. So for that, is there any nice values? -1, 1. So yeah, that. This one is in the first quadrant, so we're going to keep this example in the first quadrant. The last example we throw away the first quadrant, but this one we need to keep it. Right. X equal to 0, y equal to 0, x equal to 1, y equal to 1, and there is then any other nice values. Nope. Oh yeah. When x equal to 8, y equal to 4, and also there is an intersection because the y values are the same. X equal to 8, y equal to 4. So we have y equal to x to the 2/3, and then y equal to x minus 4. Y equal to x minus 4, this is easy, linear function. When x equal to 1, x equal to 0, y equal to -4, x equal to 4, y equal to 0. And we know that the intersection is 8 and 4. So note that this one is in the first quadrant. So we only talk about this region here. Now, let's see the point here, because obviously 0, and this is 4, and this is 8. So those are the points. Right, now we find the area. Now, two ways to do that. Again, using dx, and then we're using dy. So let's look at with the dx first. So if it is dx, we need the function above minus the function that is below, upper function minus lower function. Right, so let's look at this. Above, obviously the function, upper function is that curve. But the boundary, the lower boundary, from 0 to 4, the boundary is this equation, the x-axis, or y equal to 0. So from 0 to 4, the boundary is different. The curve on top, horizontal line at the bottom. From 4 to 8, boundary is different. One on top, and the bottom is the curve. So, in that case, we have to split the integral. Let's go from 0 to 4. From 0 to 4, we have the function on the top, x to the 2/3. The function below, horizontal line, 0. That is dx. And then from 4 to 8, the function above is x to the 2/3. The function below is x minus 4. Right. So there are two integrals because there are two boundaries. If we have one on the top, one at the bottom, that is only one integral. Likewise, one on the right, one on the left, one integral. When we have more than one boundary, we're going to need more than one integral. Right. And do all of this. Let's see what we have. Math number 9. Oops. Math number 9. I'd go from 0 to 4 of x to the 2/3, 2 over 3. First one just dx, that minus 0, gone. And then integral from 4 to 8. I have x to the 2/3. And then minus x minus 4. And do all that. So I have 11.2. Right, just going to keep it like that. Now, try the same thing. And 4. Y equal to x to the 2/3. And then y equal to x minus 4. And of course we still have this written. But now we set up the integral using dy, meaning that when we look at this, we know the point here is 8 and 4. So in terms of this region, the y values go from 0 to 4. That's for the y values, because we're going to use dy. So we know the limit though. 0 to 4. Right. So what will be in here? So let's look. If we're going to use dy, it's going to be left and right. So as you see, there's a consistency here. The region bounded on the left by the curve and bound the right by the curve. One boundary on the left, one boundary on the right. We need one integral. At least that part we're sure. But what do we put in here? Right. So whatever we put in here, it cannot be x. It can only have y or constant is still fine, but it cannot be x. So we're not going to put x to the 2/3 here. That could be wrong. Everything here have to be in terms of y. Right. So now if we have x equal to 2/3, y equal to x to the 2/3, how do we write this in terms of x equal to something of y? So what we do is we try to get back into x. So what we do is we raise both sides to the reciprocal power of 3/2. Of course, we do that both sides. 2/3 times 3/2, that is 1. So we just have 1. And then y to the 3/2. So equivalently, y equal to x to 2/3. Equivalently, we can say x equal to y to the 3/2. The other one is easy though. Y equal to x minus 4 plus 4 on both sides. X equal to y plus 4. So what we see is the function on the right is the line. And we write that in terms of y. Subtract the function on the left in terms of y. So let's do integral math, option number 9, from 0 to 4, y plus 4. We can just use x, but I just use y to the 3/2. The variable is y. As you see, they should be the same, except for the calculating error here. Right. So whether we set up like that or that, we should get the same area. But once again, if we use x, dx, then we're going to have the function above minus the function below. So I'm going to write the note here. So if we're going to use dx, because dx is horizontal, if we want the area, it is going to be that distance that is the function above minus the function that is below, upper minus the lower function. In that case, we have the area of rectangles, kind of rectangle, but just do that. Now, likewise, if we use dy, that is going to be vertical. Dy is vertical. If we want this area, we're going to need this measure, which is the one on the right minus the one on the left. So pretty much we try to get the area. Let's think about that like the area of rectangles. If we have dx, we need a vertical component. If we have dy, we need to have the horizontal component of it. The horizontal component, right minus left. The vertical component, upper function minus lower function. So that's how we get the area between two curves. Right. Next, in this example, we try to sketch and find the area bounded by y equal to cosine of x, y equal to sine x from here to there. Right. Usually, if we want to find the area, in this case, the way we do that, the simple trick is we know the integral from pi over 4 to 5 pi over 4. So that part's easy. What we need to determine is which one above, which one below. What if we don't know? I said we don't even need to know. If we just want the area, in that case, we can just say, by the way, is this in radian? It is. We just say it goes from pi over 4 2 5 pi over 4. And the function, we don't know which one above, which one below. If we just want to estimate the area, I will use absolute values. And I'll just say, just pick one. How about cosine of x minus sine x? I said it doesn't matter. Because of the absolute values, it guarantees it to be positive. So if we try to find the area bounded by two functions, and they give you the boundary, yeah, just absolute values. That certainly works. And so that's the answer. That looks like 2 square root of 2. But, right, now they actually want us to sketch. So why don't we sketch? Y equal to cosine of x. And then y equal to sine x. That's nice and all, but it doesn't tell us much. If we want that to graph it perfectly, look like we go from pi over 4 to 5 pi over 4. So it is wise just to graph from, let's say, from 0 to 2 pi. So I hit Windows, and I would say, how about x go from 0 to 2 pi. And here it increment the scale for each increment. How about pi over 4? Because we have pi over 4 here. Right, y values. This is just sine, cosine. We don't need that much. Sine, cosine is only between -1 and 1. So why don't we just say -2 to 2? Right? And then the graph will look a lot better. So not only we know that it goes from 0 to 2 pi, we know it tick is pi over 4. So 1 up pi over 4, 2 pi over 4, 3, 4, and 5 pi over 4. So let's say this is 1 and -1. So y equal to cosine of x. So from 1, 0, so that is cosine. And now the y go to sine x. The curve is going to be like this. Obviously, the sine x is above cosine of x. And since we choose each tick to be pi over 4, so we have pi over 4 is this point, and 2 pi over 4, 3, 4, 5 pi over 4. So the integral here from pi over 4 to 5 pi over 4. The function above is sine x. The function below cosine x. And we just integrate. Integral of sine is negative cosine. Integral of cosine is negative. Integral of cosine is sine. Going from pi over 4 to 5 pi over 4. Right, put 5 pi over 4 in. And then put pi over 4. cosine of high pi over 4 is a little more. Okay, we can just look real quick. Cosine of high pi over 4, both of them are negative. The value is square root of 2 over 2. And then cosine pi over 4, both of them are positive. So square of 2 over 2, because that's like 45 degrees. So what we have here is negative square of 2 over 2 minus that plus square of 2 over 2. Then minus, so that plus square root of 2 over 2, and then plus another square root of 2 over 2, because minus negative. So let's see how many of those. 1, 2, 3, 4. So there are 4 of them. Cancel the 2. So this is 2 square root of 2. As mentioned before, the integral, so that look like 2 square root of 2. Right. I said, I just want to note that if we just want the values, it doesn't matter. Just throw in the absolute values. Even it is cosine of x minus sine x, it doesn't matter, because absolute values guarantee it to be positive. Right. But that's just an approximation. If we want to do it by hand, make sure that indeed a function above minus the function below, or the function on the right minus the function on the left. You cannot use the absolute values if we're going to do that by hand. Right. Next, we're trying to find the area bounded by those 3 functions. Y equal to a minus 2x. Right. Linear function, so we just need 2 distinct points. X equal to 0, y equal to 8. How about 1? Then will be 6, 0 and 8, 1 and 6, and then 2 will be 4, and then so on. And y equal to x plus 8, so also another linear function. X equal to 0, y equal to 8, x equal to 1, y equal to 9. Right. So on this one, of course, also y equal to 0, the x-axis. So we're talking about this area here. So let's use in both from dx and then dy. So now if we want to use dx, let's look at dx. If this is dx horizontal, so we need the vertical component. The vertical component of it will be the function above minus the function below. Upper function minus the lower function. So if we look at this, below the function, the lower function y equal to 0, so that's simple. But above, they're bounded by two functions. One is this line and the other one is this line. So there are two boundaries on the top, one boundary at the bottom. So in that case, we need two integrals, one of which from here to here, and one of the other will be from here to there. Right. Also need to know the points. So this point, obviously, when y equal to 0, x equal to -8. So we have -8. And then this point, when the y equal to 0, x equal to 4. So from 0, -8 to 4. But we have to split right here. So the integral will go from -8 to 0, where the function above is x plus 8. The function at the bottom, y equal to 0. And then plus integral will go from 0 to 4. The function that is above, a minus 2x. Subtract the function below the x-axis, y equal to 0. So if we use dx, that's what we do. That. Now if we want to use dy, meaning we're going to use the function on the right and function on the left. So if we look at horizontally, the horizontal component, on the right we have y equal to x, a minus 2x. On the left we have y equal to x plus 8. So notice that it's only one function on the left, one function on the right. So we only need one integral. And also the limit for y. All the y values will go from 0 to 8. So limit from 0 to 8. Right, the function on the right, we cannot just put 8 minus 2x here, because y is a variable. Whatever we put in here cannot be x, cannot put x in this integral. Right, so we have to move things around. If y equal to a minus 2x, equivalently we solve for x minus 8 and divide by -2 equal to x. And split this. So we have y over -2 or -1/2 y, or -y over 2 plus 4 equal to x. So we have to use that function on the right. And then this function, if we want to solve for it, x equal to y minus 8. And we're going to use this function on the left. Notice that all of that has to be in terms of y. We cannot put x when we have dy. And because we cannot put y in terms of dx. So be mindful of that. If we're going to use dy, convert all the function to y. Right. After all of that, the answer is, of course, we don't even need any calculus to this, because after all, we're trying to find the area of a triangle, which is just 1/2 base times height. So 1/2 the base from -8 to 4, that will be 12 units. The height from 0 to 8. So that's 6 times 8 is 48. So don't, because bottom line is we still just find the area. So if it is something just like triangle, yeah, we don't even need to set up the integral for it. So that's what we have for this one. Next, sketch and then set up the function, and then using both dx and dy. Right, so let's sketch. Y equal to e to the x. What's that look like? Previous section, we know that the exponential function e to the x goes to infinity very fast. By the way, we need to go back to the standard windows. Hit zoom number 6 to get to the standard windows. Right, exponential function go to infinity very fast. How about the table though? X equal to 0, y equal to 1, because anything raised to 0 power is 1, except for 0. When x equal to 1, this is e to the first, which is just e, and e is approximately equal to 2.71828, so about here. And then when x equal to 2, will be 7.389, let's say 7.39, approximately equal to. So this is the exponential function. Oops. I said it go to infinity very fast. Faster than any polynomial function. Right. Right. Now, y equal to 1, so that's easy. And x equal to 2, which is the vertical line. Right. And then on this one, if we want to use dx, we need the vertical component. The vertical component, the function above minus the function below. So in this case, it will be very easy. The function above is e to the x. We need x though. And the function below is just 1. And in this case, just go from 0 to 2. So we just have that. Simple enough. If we have dx, we need the vertical component, which is the function, upper function minus the lower function. So I have e to the x, y equal to 1, and x equal to 2. So exactly the same thing. This time we use dy. Now let's look at this. In terms of dy, we need the horizontal component. Once again, where's the summary? Okay. So if we have dx, we need the vertical component above the upper function minus lower function. If we have dy already, we're going to need the horizontal component, the function on the right minus the function on the left. Right. So the function on the right is x equal to 2. We cannot put x in it if it is dy. But we do know the limit. Actually, worry about that later. We know the limit is whatever the values here, which is 1, and go up to whatever the values there. But we know that this point when x equal to 2, y equal to about 7.39. So that, in that case, we say just e square would be the values for y. Right. One function on the left, one function on the right. The function on the left is 2. I'm sorry. The function on the left is e to the x. The function on the right is 2. So we just have 2 to subtract. We cannot put e to the x here because this is dy. So everything has to be in terms of y. Right. So y equal to e to the x. How do we write that? As x equal to something of y, so or the inverse function, if you will. So to get rid of the exponential, we use the log or the ln, because those are inverse function of each other. So we take ln on both sides, and ln of y, just ln of y. Ln of e cancel out, we just have x. So x equal to ln of y, and we're going to put a function of y in here. So either that or that, the area here should be equal each other. Right. Example 3. Now we do the same thing. Sketch and set up the integral with respect to x and with respect to y. So both dx and dy. Right. So first I sketch y equal to x squared. That is the parabola. And then x equal to 2. When x equal to 0, y equal to 2, when x equal to 1, y equal to 3, and so on. So we talk about this area. So now if we use dx, need the vertical component, upper function minus lower function. So this region, it is bounded above by that. I should not want that. I should make a good use of that. So the function above is x plus 2, the function below is x squared. So we just have 1 on the top, 1 on the bottom. That's why we only need one integral. From -1 to 2. The function on the top, x plus 2. The function at the bottom, x squared. So 1 on the top, 1 at the bottom. So we only need one integral. And pretty much that. Now let's try to do this in terms of y, which will be a little more complicated. By the way, and then you say, why do we know negative 1 and 2? Well, if we want to solve for those points, we just make them equal. Both of them equal to y. So why don't we make them equal each other? Move this to the other side. X squared minus x minus 2 equal to 0. And now we just solve for x. That should be simple, right? Quadratic equation. Solve for that. We should have negative 1 and 2. Now, if we're going to use dy, we need the horizontal component. So that is the region, and there's a big problem because this region on the right, it is bounded by parabola, which is good, but on the left it is bounded by the parabola, even the same function. That makes things interesting. And then the y equal to x plus 2. So 2 boundary on the left, 1 boundary on the right. So we need 2 integrals. Something minus something. And then something minus something. Right, so we need 2 integrals because there are 2 boundaries on the left. So where do we split? Well, we'll split right here. Because from here, it has the integral from x plus 2 and then x squared. But at the bottom, it is bounded by the left by the parabola, on the right also by the parabola. Right, so but first, y equal to x squared. If we want to solve for x, it is easy. Take square root both sides. So plus or minus square root of y equal to x. So notice that we have 2 functions, one of which is on the right side. So I have to change something here. Let's use purple. On the right, we have x equal to positive square root of y. And on the left, it is x equal to negative square root of y. So that's why we have a positive and a negative. Now if we want to split, it will be right here, which is 1. X equal to negative 1, y equal to 1. So we go from 0 to 1 for y. And from 0 to 1, the one on the right is square root of y. The one on the left, negative square root of y. And then from 1 to 4, then this is 1, and that is the point 2 and 4. So we go from 1 to 4. And from 1 to 4, the function on the right is square root of y. And the one on the left is the line x plus 2. But we cannot put x plus 2 in there. Remember, it has to be in terms of y. So, simple enough. Y equal to x plus 2, so x equal to, subtract 2 on both sides. Remember, what we put in here for dy has to be in terms of y. Cannot put x there. Right, and with that, we finish section 6.2. Thank you for watching.